Hey everyone, welcome back to DataBits Central, your hub for mastering data science and coding. Today, we will embark on a journey, focusing on a new aspect: how to keep track of the different versions of your code and configuration files using version control systems or VCSs. It will allow us to easily roll back when mistakes happen and also help us collaborate with others. You might have already heard of version control systems in the context of managing configuration files or maintaining the source code of programs and scripts. This is your next big skill. So hit that like button if you're ready, grab a drink, and let's dive into Git and GitHub. In this video, I'll introduce you to a popular VCS called Git and show you some of the ways you can use it. We'll also go through how to set up an account with a service called GitHub so that you can create your very own remote repositories to store your code and configuration. By the end of this guided video, you'll be able to store your code's history in Git and collaborate with others in GitHub. Let's get started. Nowadays, lots of employers will ask to see your GitHub portfolio when you're interviewing for IT roles. GitHub portfolios give companies an idea of what projects you've worked on and what kind of code you can write. This course will help you get your setup. Let's kick off with Git. It's free, works on Windows, Mac, and Linux. But what is version control? A version control system keeps track of the changes that we make to our files. By using a VCS, we can know when the changes were made and who made them. It also lets us easily revert a change if it turned out not to be a good idea. It makes collaboration easier by allowing us to merge changes from lots of different sources. VCSs let us retrieve past versions of the file or directory and see who changed which files, how each file was changed, and when the file was changed. On top of this, we can make edits to multiple files and treat that collection of edits as a single change, which is commonly known as a commit. A VCS even provides a mechanism to allow the author of a commit to record why the change was made, including what bugs, tickets, or issues were fixed by the change. This information can be a lifesaver when trying to understand a complex series of changes or to debug some obscure issue. So, be sure to record this extra info in your commits to be truly committed to better code. A version control system can be used to store much more than just code. We can use it to store configuration files, documentation, data files, or any other content that we may need to track. A VCS stores your code and configuration. It also stores the history of that code and configuration. A version control system can function a lot like a time machine, giving you insights into the decisions of the past. Git is a VCS. It's a free open source system available for installation on Unix-based platforms, Windows, and Mac OS. Git is now one of the most popular version control systems out there and is used in millions of projects. Unlike some version control systems that are centralized around a single server, Git has a distributed architecture. This means that every person contributing to a repository has a full copy of the repository on their own development machines. Collaborators can share and pull in changes that others have made as they need. And because the repositories are all local to the computer being used to create the files, most operations can be done really fast. If you want to collaborate with others, it usually makes sense to set up a repository on a server to act as a kind of hub for everyone to interact with. But Git doesn't rely on any kind of centralized server to provide control organizations to its workflow. Git can work as a standalone program as a server and as a client. This means that you can use Git on a single machine without even having a network connection. Or you can use it as a server on a machine where you want to host your repository. And then you can use Git as a client to access the repository from another machine or even the same one. Git clients can communicate with Git servers over the network using HTTP, SSH, or Git's own special protocol. You can use it for small projects with like one developer or huge projects with thousands of contributors. You can use it to track private work that you can keep to yourself, or you can share your work with others by hosting a code on public servers like GitHub. We explored what Git and what version control system are. In this video, we'll cover many different things that you can do with Git. To follow along, you'll need to install Git on your computer. On top of this, I'll show you how to interact with Git through the command line. Our examples will be shown on a computer running Windows, but you can use Git on any operating system. There are versions of Git available for all popular operating systems. So before we get any further, let's get Git installed on your computer. Once it's installed, you'll be able to use it from the command line, just like any other tool. On Windows, after downloading and executing the installer, you'll need to go through a bunch of different configuration options. We'll start by downloading the latest version of the software from the git-scm.com website. All right, let's click on Download for Windows button. Then click here to download. Choose the path where you want to download the file, then Save to start download. Wait a while until download is finished. Now, click on the execution file to start installing. The first window we get is the license of the software. Git is released under the GPL version 2 license, which is a free software license. All right, let's accept this license and continue with the setup. The first option we get is the installation path. We'll keep it. This window lets us select additional components to add to our Git installation. By default, Git integrates with the Windows Explorer to let us run Git command line or the Git graphical interface in the current folder. This software bundle comes with an extension for improving the support of how large files, like audio or video files, get stored in the version control system. It's a good idea to keep this enabled. The installer will also register the Git configuration files as files that should be opened with a text editor and the .sh files as files that should be executed with bash. All of this makes sense, so we'll keep these options selected. If you want, you can also enable some of the other options that will cause the icons to be displayed on the desktop, TrueType fonts to be used in the console, or software to automatically check for updates. All right, let's keep going. We get prompted for the name of the folder where we want to create all the shortcuts. Git is fine as the name for this, so let's continue. Okay, now's the time to choose the editor. This is the option that you'll most likely want to adjust. You want to select an editor that you're comfortable with. The installer already has a list of possible options that you could choose here, like Notepad++, Visual Studio Code, or Sublime Text. And we can even select any other editor we wanted by entering the path to the editor's executable file. For this video, we'll be using Visual Studio Code in all of our examples. So let's choose VS for this installation. Heads up, the bundle doesn't ship with any of these graphical editors installed. You'll need to install the one you want separately. Okay, now we want to adjust the name of the initial branch in New Repositories. We'll keep the default selection to Let Git Decide. All right, we're now asked to choose how we want to adjust the path environment. This option lets us decide how we want to execute Git from the command line. Selecting the first option will make Git only accessible through the embedded command line that is shipped with the bundle. The second option, the one that's pre-selected, allows us to execute Git from the embedded command line and from the Windows command prompt. The third option will add the Unix-like tools shipped together with Git to the Windows command prompt. If you choose this option, any commands that have the same name as those in the OS will then come from the bundle and not the basic OS. We'll keep the second option selected, as it's the one that's most convenient for us, while not interfering with the local tools. In the next window, to choose which secure shell we would like Git to use, we will keep the chosen option to use ssh.exe that comes with Git. This window lets us choose how we want to validate the SSL certificates used for HTTPS connections. We can choose to use the OpenSSL library that's shipped together with Git, or use the native Windows library. You'll want the second option if you need to interact with your company's internal systems. As we'll only be interacting with GitHub, we'll choose the first option here. This window lets us select what we want to do about line endings. The characters used to indicate the end of a line are different between Windows, Linux, and Mac OS. So the Git software bundle lets us decide how we want to handle these differences. The default is to store Windows line endings on the local files, but use Unix line endings in the files stored by Git. This works well when you're using your Windows computer to collaborate with others using a different OS. The second option is to keep the line endings unchanged when copying the files locally, and use Unix line endings for the files stored in Git. This would work well if you're using a Unix-like OS, or if you're only editing through Unix-like editors on Windows. The third option is to not do any conversions. This option doesn't work well if you're trying to work with people using a different OS. So it's only recommended if all your collaborators will be running the same OS as you. All right, let's keep the first one selected and move on. This window lets us configure the terminal emulator. The software bundle ships with its own terminal emulator that includes a bunch of nice features, like better Unicode support and a long history of commands that we can scroll. We'll keep that one selected, but if you feel like you're more comfortable with the Windows default console window, you can choose that one. All right, we have a few extra options that we can choose to enable if we want. We'll keep these as they are. That way we'll get the performance improvements of letting Git do file system caching, and we'll be able to use Git's credential manager. We don't need to use symbolic links in our repositories, so we'll leave that disabled. We'll just click Install here to get our installation started. All right, Git is installing on our machine. It'll take a while for it to complete. Once it's done, we'll have all the Git goodness at our fingertips. Now, let's get started to learn how to use Git. We've talked about what version control is, why it's necessary. Additionally, we've learned how to install Git. Now, we will take our first steps with Git. When starting with Git, there are a bunch of concepts that we need to learn to understand how things are organized and how our files are tracked. We'll introduce some of the main Git concepts. We'll dive into all of them as we expand our Git knowledge. Let's start by setting some basic configuration. Remember when we said that a VCS tracks who made which changes? For this to work, we need to tell Git who we are. We can do this by using the git config command and then setting the values of user.email and user.name to our email and our name like this. We use the -- global flag to state that we want to set this value for all Git repositories that we'd use. We could also set different values for different repositories. With that done, there are two ways to start working with a Git repository. We can create one from scratch using the git init command, or we can use the git clone command to make a copy of a repository that already exists somewhere else. For now, let's start by creating a new directory and then a Git repository inside that directory. For example, let's use the mkdir command to create a directory called scripts, and then a Git repository inside that directory. So when we run git init, we initialize an empty Git repository in the current directory. The message that we get mentions a directory called Git. We can check that this directory exists using the ls-la command, which lists files that start with a dot. We can also use the ls-l.git command to look inside of it and see the many different things it contains. This is called a Git directory. You can think of it as a database for your Git project that stores the changes and the change history. We can see it contains a bunch of different files and directories. We won't touch any of these files directly. We'll always interact with them through Git commands. So whenever you clone a repository, this Git directory is copied to your computer. Whenever you run git init to create a new repository like we just did, a new Git directory is initialized. The area outside the Git directory is the working tree. The working tree is the current version of your project. You can think of it like a workbench or a sandbox where you perform all the modifications you want to your file. This working tree will contain all the files that are currently tracked by Git and any new files that we haven't yet added to the list of track files. Right now, our working tree is empty. Our shiny new Git repository can now be used to track changes to files inside of it. But before jumping into that, let's check out our current configuration by using the git config-l command. There's a bunch of info in there, and we won't cover all of it. For now, pay special attention to the user.email and the user.name lines, which we touched on briefly in an earlier video. This information will appear in public commit logs if you use a shared repository. For privacy reasons, you might want to use different identities when dealing with your private work and when submitting code to public repositories. We'll include more details about changing this information. Okay, our repository is ready to work, but it's currently empty. Let's create a file in this repo. We'll start with a basic skeleton for a Python script. which will help us demonstrate the Git workflow. As with any Python script, we'll start with the shebang line. For now, we'll add an empty main function, which we'll fill in later. And at the end, we'll just call this main function. All right, we've created our file. This is a script that we'll want to execute. So let's make it executable. And then let's check the status of our repo using git status command. We now have a file and a working tree, but it's currently untracked by Git. To make Git track our file, we'll add it to the project using the git add command, passing the file that we want as a parameter. With that, we've added our file to the staging area. The staging area, which is also known as the index, is a file maintained by Git that contains all of the information about what files and changes are going to go into your next command. We can use the git status command to get some information about the current working tree and pending changes. Let's check that one out. We see that our new file is marked to be committed. This means that our change is currently in the staging area. To get it committed into the .git directory, we run the git commit command. Let's try that now. When we run this command, we tell Git that we want to save our changes. It opens Visual Studio Code Editor, where we can enter a commit message. If you want, you can change the editor used to your preferred editor. In our case, this computer has Visual Studio Code configured as a default editor as we selected in the installation steps. The text that we get tells us that we need to write a commit message and that the change to be committed is the new file that we've added. For now, let's enter a simple description of what we did. We'll say that our change is creating an empty all_checks.py file, then save and exit. And with that, we've created our first Git commit. As we mentioned, that any Git project will consist of 3 sections: the Git directory, the working tree, and the staging area. The Git directory contains the history of all the files and changes. The working tree contains the current state of the project, including any changes that we've made. And the staging area contains the changes that have been marked to be included in the next commit. So it might be helpful to think about Git as representing your project, which is the code and associated files and a series of snapshots. Each time you make a commit, Git records a new snapshot of the state of your project at that moment. It's a picture of exactly how all these files looked at a certain moment in time. Combined, these snapshots make up the history of your project, and it's information that gets stored in the Git directory. Now, let's dive into the details of how we track changes to our files. When we operate with Git, our files can be either tracked or untracked. Tracked files are part of the snapshots, while untracked files aren't a part of snapshots yet. This is the usual case for new files. Each tracked file can be in one of 3 main states: modified, staged, or committed. Let's look at what each of these mean. If a file is in the modified state, it means that we've made changes to it that we haven't committed yet. The changes could be adding, modifying, or deleting the contents of the file. Git notices anytime we modify our files, but won't store any changes until we add them to the staging area. So the next step is to stage those changes. When we do this, our modified files become stage files. In other words, the changes to those files are ready to be committed to the project. All files that are staged will be part of the next snapshot we take. And finally, when a file gets committed, the changes made to it are safely stored in a snapshot in the Git directory. This means that typically a file tracked by Git will first be modified when we change it in any way. Then it becomes staged when we mark those changes for tracking. And finally, it will get committed when we store those changes in the VCS. Let's see this in action in our example Git repo. First, let's check the contents of the current working tree using ls-l, and then the current status of our files using the git status command. When we run git status, Git tells us a bunch of things, including that we're on a master branch. We'll learn about branches later. For now, notice how it says that there's nothing to commit and that the working tree is clean. Let's modify a file to change that. So let's add a bit more content to our script to see that in action. We'll add a function called check_reboot that will check if the computer is pending a reboot. To do that, we'll check if the run/reboot required file exists. This is a file that's created on our computer when some software requires a reboot. And of course, since we're using os.path that exists, we need to add import os to our script. All right, we've added a function to our file. Let's call git status again and see the new output. Again, Git tells us a lot of things, including giving us some tips for commands that we might want to use. These tips can come in real handy, especially when we're familiarizing ourselves with Git. See how the file we changed is now marked as modified, and that it's currently not staged for commit? Let's change that by running the git add command, passing the all_checks.py file as a parameter. When we call git add, we're telling Git that we want to add the current changes in that file to the list of changes to be committed. This means that our file is currently part of the staging area, and it will be committed once we run the next git command, git commit. In this case, instead of opening up an editor, let's pass the commit message using the -m flag, stating that we added a new function called check_reboot, and then pass the commit message that we want to use. So in this case, we'll say that we've added the check_reboot function. So we've now committed our stage changes. This creates a new snapshot in the Git directory. The command shows us some stats for the change made. Let's do one last status check. We see that once again, we have no changes to commit, because the change we made has gone through the full cycle of modified, staged, and committed. With that, we've demonstrated the basic Git workflow. We make changes to our files, stage them with git add, and commit them with git commit. Remember that the only way to get familiar with these concepts is practice. We've talked about what version control is, why it's necessary. We also started learning some basic Git commands and procedures. Now we'll go into much more detail about what we can do with Git. These are Git's greatest hits. We'll start by learning some handy shortcuts and looking into how we can get more info out of our version control system. Then, we'll experience the true power of Git by seeing how we can undo some of our changes, and many different techniques that we can use in Git. Let's start with the following command. Git commit -a is a shortcut to stage any changes to track files and commit them in one step. But if the modified file has never been committed to the repository, we'll still need to use git add to track it first. So let's make a change to our example script from the earlier video and try out this new flag. We'll now modify our main function and make it call the check_reboot function that we wrote before. If a reboot is pending, we'll print a message and then exit our program with an exit status of 1. Since we're using the sys module, we'll need to import it. Alright, now that we've made the change, we're ready to try out the new -a flag. We'll also use the -m flag to add the commit message directly. This time, we'll say that we're calling check_reboot and exiting with 1 on the error condition. These shortcuts are useful when making small changes that we know we'll want to commit directly without keeping them in the staging area and having to write long and complex descriptions. Keep in mind that when you use the -m shortcut, you can only write short messages. So it's best reserved for truly small changes that don't require extra context or explanation, short and sweet. Heads up, when you use the -a shortcut, you skip the staging area, meaning you can't add any other changes before creating the commit. The commit will show up in the log along with the message, just as usual. Let's check that out with git log command. See how our latest commit was added to the top of the list of commits, and notice how the head indicator has now moved to the latest commit. You might be wondering, what is this head and where is it heading? Git uses the head alias to represent the currently checked out snapshot of your project. This lets you know what the contents of your working directory should be. In this case, the current snapshot is the latest commit in the project. We can even use Git to go back in time and have head representing old commit from before the latest changes were applied. In all cases, head is used to indicate what the currently checked out snapshot is. This is how Git marks your place in the project. Think about it as a bookmark that you can use to keep track of where you are. As a shortcut, it's generally easy to think of head as a pointer to the current branch, although it can be more powerful than that. Next, we'll dig into how we can get more information about our changes, both before and after we commit them. We've seen how Git log shows us the list of commits made in the current Git repository. By default, it prints the commit message, the author, and the date of the change. This is useful, but if we're combing through a history of changes in a repo to try and find what caused the latest outage, we'll probably also need to look at the actual lines that changed in each commit. To do this with Git log, we can use the -p flag. The P comes from patch, because using this flag gives us the patch that was created. Let's try it out. It shows added lines with pluses and remove lines with dashes. Because the amount of text is now longer than what fits on your screen, Git automatically uses a paging tool that allows us to scroll using page up, page down, and the arrow keys. We still have one commit below the other, but now each commit takes up a different amount of space depending on how many lines were added or removed in that commit. Using this option, we can quickly see what changes were made to the files in our repository. This can be especially useful if we're trying to track down a change that recently broke our tools. If we don't want to scroll down until we find the commit that we're actually interested in, another option is to use the git show command. This command takes a commit ID as a parameter and will display the information about the commit and the associated patch. Remember that this is an identifier that we see next to the word commit in the log. Let's check this out by first listing the current commits in the repo and then calling git show for the second commit in the list. Another interesting flag for git log is the --stat flag. This will cause git log to show some stats about the changes in the commit, like which files were changed and how many lines were added or removed. Let's try it with our repo. Now, what about changes that haven't been committed yet? Until now, whenever we've made changes to our files, we've either added them to the staging area with git add and committed them with git commit, or committed them directly using git commit-a. This works fine, but it means we have to know exactly which changes we've made. Sometimes it can take a while until we're ready to commit. But imagine you've been working on adding a new complex feature to a script and it requires thorough testing. Before committing it, you need to make sure that it works correctly. Check that all the test cases are covered and so on and so on. So while doing this, you find bugs in your code that you need to fix. It's only natural that by the time you get to the commit step, you don't really remember everything you changed. To help us keep track, Git gives us the git diff command. Let's make a new change to our script and then try this command out. We'll add another message to the user to say that everything is okay when the check is successful and then exit with 0 instead of 1. Okay, we've made the change. Let's now save it and check out what git diff command shows us. In this case, we see that the only change is the extra lines that we've added. If our change was bigger and included several files, we could pass a file by parameter to see the differences relevant to that specific file instead of all the files at the same time. Something else we can do to review changes before adding them is to use the -p flag with the git add command. When we use this flag, Git will show us the change being added and ask us if we want to stage it or not. This way we can detect if there's any changes that we don't want to commit. Let's try that one out. We've staged our change, and it's now ready to be committed. If we call git diff again, it won't show any differences since git diff shows only unstaged changes by default. Instead, we can call git diff --stage to see the changes that are staged but not committed. With this command, we can see the actual stage changes before we call git commit. Let's commit these changes now so that they aren't pending anymore. We'll say that we've added a message when everything's okay. Nice. And with that, we've learned a bunch of different ways to get more information about our changes. Let's say that you've decided to clean up some old scripts and want to remove them from your repository. You can remove files from your repository with the git rm command, which will stop the file from being tracked by Git and remove it from the Git directory. So you'll need to write a commit message as to why you've deleted them. Let's try this out in our checks repository that contains a file we decided we actually don't want. We'll first look at the contents of the directory with ls, then delete the file with git rm, then check the contents with ls again, and finally check the status with git status. Let's do that now by calling git commit and setting a message indicating that we've deleted the unneeded file. As usual, we get a bunch of stats when we do the commit. Check out all the deletions it reported. These are all lines in the file that are no longer there, and it states the file itself was deleted. You can use the gitmv command to rename files in the repository. Let's rename our existing script to checkfreespace.py, and then check what git status has to say about that. The status shows us that the file was renamed and clearly displays the old and new names. As with the previous example, the change is staged but not committed. Let's commit it by calling git commit once again. The mv command can be used for both moving and renaming. If our repository included more directories in it, we could use the same git mv command to move files between directories. The output of git status is a super useful tool to help us know what's up with our files. It shows us which files have tracked or untracked changes and which files were added, modified, deleted, or renamed. It's important that the output of these commands stays relevant to what we're doing. If we have a long list of untracked files, we might lose an important change in the noise. If there are files that get automatically generated by our scripts, or our operating system generates artifacts that we don't want in our repo, we'll want to ignore them so that they don't add noise to the output of git status. To do this, we can use the git ignore file. Inside this file, we'll specify rules to tell Git which files to skip for the current repo. For example, if we're working on an OS X computer, we'll probably want to ignore the .ds store file, which is automatically generated by the operating system. To do this, we'll create a .gitignore file containing the name of this file. Remember that the dot prefix in a Unix-like file system indicates that the file or directory is hidden and won't show up when you do the normal directory listing. That's why we have to use ls-l to see all files. We've added a gitignore file to our repo, but we haven't committed it yet. This file needs to get tracked, just like the rest of the files in the repo. Let's add it now. Done, and it looks great. We learned how to interact with Git using some handy shortcuts. Now, we'll talk about the most common ways to revert changes in Git and when to use each approach. Being able to revert our changes is one of the most powerful features offered by version control systems. There's a bunch of different techniques available depending on which changes we need to undo. For example, you might find yourself in a situation where you've made a bunch of changes to a file, but decide that you don't want to keep them. You can change a file back to its earlier committed state by using the git checkout command followed by the name of the file you want to revert. Speaking of, let's try this out using our scripts repository. We'll edit our all-checks.py script and remove the check reboot function, then save and go back to the command line. We've made our change. Let's try our script and see what happens. As expected, we see that our file is modified and the changes aren't staged yet. Check out how Git gives us a couple helpful tips on what to do now. We can run git add to stage our changes, or we can run git checkout to discard them. Let's do that now. We'll check out the original file, and then take a look at what git status has to say about it, and finally retry our script. Looks like we have a typo. Let's go back and fix it. Done and done. With that, we've demonstrated how we can use git checkout to revert changes to modify files before they get staged. This command will restore the file to the latest storage snapshot, which can be either committed or staged. So if you've made additional changes to a file after you've staged it, you can restore the file to the earlier stage version. If you need to check out individual changes instead of the whole file, you can do that using the -p flag. This will ask you change by change if you want to go back to the previous snapshot or not. That's it for undoing unstaged changes. What if you added the changes to the staging area already? If we realize we've added something to the staging area that we didn't actually want to commit, we can unstage our changes by using the git reset command. Staging changes that we don't actually intend to commit happens all the time, especially if we use a command like git add star, where the star is a file glob pattern used in Bash that expands to all files. This command will end up adding any change done in the working tree to the staging area. While sometimes that might be what we want, it can also lead to some surprises. Let's try it out with an example. First, we'll pretend we're trying to debug a problem in our script. For that, we create a temporary file with the output of our script. Then, we'll add all unstaged changes in our working tree using git add star. Finally, check the status using git status. We can see that this output file, which was supposed to be a temporary file for debugging, has now been staged in our repo, but we didn't want to commit it. Conveniently, the git status command tells us how to unstage the file right there in the output. The example output mentions the head alias. Remember what that means? That's right. It's the current checked out snapshot. So by running the suggested command, we're resetting our changes to whatever's in the current snapshot. Let's try it out. The file is once again untracked in our working tree and no longer staged. You can think of reset as the counterpart to add. With add, you can add changes to the staging area. With reset, you remove changes from the staging area. You can use git reset -p to get Git to ask you which specific changes you want to reset. Get it? But wait, let's remember to commit our typo fix. With that, we've seen how we can revert unstaged and staged changes. But what if you've already created a commit with the changes that you want to undo? Let's say you just finished committing your latest batch of work, but you've forgotten to add a file that belongs to the same change. You want to update the commit to include that change. We can solve problems like these using the -- amend option of the git commit command. When we run git commit -- amend, Git will take whatever is currently in our staging area and run the git commit workflow to overwrite the previous commit. Let's see this in an example. We'll go to our scripts directory and create 2 new files using the touch command. Then list the contents of the directory using ls at our Python script and commit it saying that we've added 2 files. As you can see, the message printed by Git says that only 1 file was added. Our commit message said that we added 2 files, but we forgot to add one of them. We can fix it. We'll start by adding the missing file and then amending our commit. We called git commit -- amend, and an editor opened up showing the commit message and the stats about the commit that we're working with. The list of added files for this commit now includes both files that we wanted to add. Yay! Now that the files have been added, we can also improve our initial commit message, which was a bit too short. We'll keep the existing description as the first sentence of our commit, and then add a line of description about the intended purpose of each file. With that, our commit is ready to be amended. Let's save a new description as usual. We've amended our previous commit to include both files and a better message. You could also just update the message of the previous commit by running the git commit -- amend command with no changes in the staging area. An important heads up, while git -- amend is okay for fixing up local commits, you shouldn't use it on public commits. Meaning, those that have been pushed to a public or shared repository. This is because using --amend rewrites the Git history, removing the previous commit and replacing it with the amended one. This can lead to some confusing situations when working with other people and should definitely be avoided. So remember, fixing up a local commit with amend is great, and you can push it to a shared repository after you fixed it. But you should avoid amending commits that have already been made public. Fixing your work before you commit is good. But what happens if it's already been snapshot by Git? Let's say you host a Git repository on a company server that contains all kinds of useful automation scripts that you and your coworkers use. One morning before coffee, you make a few changes to one of these scripts and commit the updated files. A few hours later, you start to receive tickets from users indicating some part of the script is broken. From the errors they describe, it sounds like the problem is related to your recent changes. You could look at the code you updated to see if you can spot the bug. But more tickets are pouring in, and you want to fix the problem as fast as possible. You decided it's time for a rollback. There are a few ways to roll back commits in Git. For now, we'll focus on using the git revert command. Git revert doesn't just mean undo. Instead, it creates a commit that contains the inverse of all the changes made in the bad commit in order to cancel them out. For example, if a particular line was added in the bad commit, then in the reverted commit, the same line will be deleted. This way you get the effect of having undone the changes, but the history of the commits in the project remains consistent, leaving a record of exactly what happened. So git revert will create a new commit that is the opposite of everything in the given commit. We can revert the latest commit by using the head alias that we mentioned before. Since we can think of head as a pointer to the snapshot of your current commit, when we pass head to the revert command, we tell Git to rewind that current commit. To check this out, we'll first add a faulty commit to our example repo. We've added some code to our script. Let's save and commit this. Let's run our script to see what happens. Oops, we used a function that we forgot to define. Okay, it's rollback time. Let's get rid of this faulty code by typing git revert head. So once we issue that git revert command, we're presented with the text editor commit interface that we've all seen before. In this case, we can see that Git has automatically added some text to the command, indicating it's a rollback. The first line mentions that it's reverting the commit we just did called add call to disk full function. The extra description even includes the identifier of the commit that got reverted. While we could use this description as is, it's usually a good idea to add an explanation of why we're doing the rollback. Remember that the goal of these descriptions is to help our future selves understand why things happen. In this case, we'll explain that the reason for the rollback is that the code was calling a function that wasn't defined. Once we're done entering the description, we can exit and save as usual. You'll notice the output that we get from the git revert command looks like the output of the git commit command. This is because git revert creates a commit for us. Since a revert is a normal commit, we can see both the commit and the reverted commit in the log. Let's look at the last two entries in the log using -p and -2 as parameters. As demonstrated before, the -p parameter lets us see the patch created by the commit, while the -2 parameter limits the output to the last two entries. So in this log, we can see that when we called revert, Git created a new commit that's the inverse of the previous one. This removes the lines that we added in the previous commit. We can see that the original commit shows the lines we added by preceding them with a plus sign. The same line shows up with a minus sign in the newer commit message indicating that they were removed. Just like that, the bad commit is reverted and the error stopped. In this example, we reverted the latest commit in our tree. But what if we had to revert a commit that was done before that? In our bad snapshot example, The error also happened to be in the most recently created commit, but errors can sometimes take a while to be detected. And so, we might need to revert other commits farther back in time. We can target a specific commit by using its commit ID. We've seen commit IDs a few times already. They show up when we're running the git log command, and we also saw the commit ID of the reverted commit in our last example. Commit IDs are those complicated-looking strings that appear after the word commit in the log messages. Let's have a look at the latest log entry in our checks repo. The commit ID is the 40-character long string after the word commit. You really can't miss it. This long jumble of letters and numbers is actually something called a hash, which is calculated using an algorithm called SHA-1. Essentially, what this algorithm does is take a bunch of data as input and produce a 40-character string from the data as the output. In the case of Git, the input is all information related to the commit, and the 40-character string is the commit ID. How can you use commit IDs to specify a particular commit to work with, like during a rollback? Let's look at the last two entries in our repo using the git log -2 command. First, let's look at that specific commit using git show, which we mentioned earlier this video. We've copied and pasted the commit ID that we wanted to display, and that works. Alternatively, we could provide just the first few characters identifying the commit to the command, and Git will be smart enough to guess which commit ID starts with those characters. Let's try this out. 2 characters is not enough, but usually 4 to 8 characters will be plenty. All right, now we've managed to identify a commit. Well done. We've only briefly mentioned branches. Branches are an important part of the Git workflow, so we'll branch out and explore them more. We'll also explore merging. Merging is the term that Git uses for combining branch data and history together. You might remember that we talked about branches in the context of the head pointer. So what is a branch? What is it used for? In Git, a branch at the most basic level is just a pointer to a particular commit. But more importantly, it represents an independent line of development in a project, of which the commit it points to is the latest link in a chain of developing history. The default branch that Git creates for you when a new repository initialized is called master. All of our examples and development have taken place on this branch so far. The master branch is commonly used to represent the known good state of a project. When you want to develop a feature or try something new in your project, you can create a separate branch to do your work without worrying about messing up this current working state. Branches make it really easy to experiment with new ideas or strategies in projects. When you want to add a feature or fix something, you can create a new branch and do your development there. You can merge back into the master branch when you've got something you like, or discard your changes without negative impact if they don't work out. In Git, branches are used all the time as a part of the normal development workflow. As an example, think back to the problematic commit we fixed earlier. We added a call to the disk full function, but forgot to actually define the function. So we had to roll it back because our users were seeing errors. Knowing what we know now, we could have done that work on a separate branch, maybe called something like add disk full. In that case, we could have iterated on our code there until it was working correctly without it affecting the master branch. Only after the code is ready to be deployed, we would merge those changes back into the master branch. We'll look into how to create new branches and merge their content into the master branch. We'll also go over what to do if you run into any scary merge conflicts. Heads up, this is about to get pretty complicated. As branches are essential to how work is done in Git, there's tons of different ways to work with them. We can use the git branch command to list, create, delete, and manipulate branches. Running git branch by itself will show you a list of all the branches in your repository. Let's try it out in our checks repo. Our list is looking pretty empty right now, but don't worry. Creating a branch is a snap. We do it by calling git branch with the name of the new branch. Let's create a new feature branch and then list the branches again with git branch. Our new branch was created based on the value of head. Remember that this might not necessarily be the master branch. The list we get shows that we're still on the master branch. We can tell because the current branch is indicated in the command's output with an asterisk in a different color. We'll look into other things that git branch lets us do with branches later on, but right now we want to switch to a new branch. To do that, we'll need to use the git checkout command. We saw earlier how we can use git checkout to restore a modified file back to the latest commit. Checking out branches is similar in that the working tree is updated to match the selected branch, including both the files and the git history. It might help to remember that we use git checkout to check out the latest snapshot for both files and for branches. All right, let's switch to our new feature branch by calling git checkout new feature and then listing our branches once again. Before we were working on the master branch, but now that we've changed to our new branch, the star has moved to a new feature. Creating a branch and switching to it immediately is a pretty common task. So common that Git gives us a useful shortcut to create a new branch and to switch to it in a single command. We can use the git checkout -b new branch to do this. Take a look. See how the message says that we've switched to a new branch? Git created a new branch and switched to it in just one command. Super efficient. Now that we have our shiny new branch, let's create a new file in. We'll create a new Python 3 file that will include the usual shebang line, an empty main function, and a call to that function. This file is empty because it's only the beginning of our work. As it's in a separate branch, it's okay for it to not be finished yet. Let's save our file and commit it to the current branch. Now, we've added a commit in this branch, and it's looking better. Let's check the last 2 entries in the log. We see the last 2 commits in this branch. Notice how next to the latest commit ID, Git shows that this is where head is pointing to and that the branch is called even better feature. Next to the previous commit, Git shows that both the master and the new feature branches are pointing to that snapshot of the project. In this way, we can see that the even better feature branch is ahead of the master branch. With that, we've seen how we can create new branches and commit changes to them. We created a new branch different than the master branch and added a commit to it. Let's check out the current status of our repo by calling git status and ls-l. So we see that we're on a clean working tree in the even better feature branch and that a new free memory.py file is in our working tree. Let's now change back to the master branch using git checkout master and then list the latest 2 commits there. When we switch to a different branch using git checkout, under the hood, Git changes where head is pointing. Thanks to this checkout, head went from pointing to the latest commit in the even better feature branch to the most recent commit of the master branch. The commit from even better feature doesn't show up at all, and the latest snapshot is the second entry we've seen before. Remember that when we switch branches, Git will also change files in our working directory or working tree to whatever snapshot head is currently pointing at. Let's look at the current contents of our directory. Free memory.py isn't there. This demonstrates that when we switch branches in Git, the working directory and commit history will be changed to reflect the snapshot of our project in that branch. When we check out a new branch and commit on it, those changes will be added to the history of that branch. One thing to note after all this back and forth is that each branch is just a pointer to a specific commit in a series of snapshots. It's very easy to create new branches because there isn't any data that needs to be copied around. When we switch to another branch, we check out a different commit and Git updates both head and the contents of our working directory. Okay, we've now seen how to create and switch between branches. So what if we want to delete a branch that we don't need anymore? We can do that by using git branch -d. Let's first list the current branches in our repo and then get rid of the new feature branch by calling git branch -d new feature. Just like that, our branch was trimmed. We can check with another call to git branch that is not there anymore. If there are changes in the branch we want to delete that haven't been merged back into the master branch, Git will let us know with an error. Hopefully, Git also gives us the command to run if we were sure that we wanted to delete the branch, even if it has unmerged changes. But we won't do that just yet. We actually want to merge those changes back into the repo first. How do we do that? Merging is the term that Git uses for combining branch data and history together. We'll use the git merge command, which lets us take the independent snapshots and history of one Git branch and tangle them into another. Let's try this out with our example branch. First, we'll check that we're in the master branch, and then we'll call git merge even better feature to merge the even better feature branch into the master branch. Now we've brought the master branch up to speed, which we can see by looking at the git log. As we're on the master branch head points at master, we can see the even better feature and master branches are now both pointing at the same commit. From time to time, we might find that both the branches we're trying to merge have edits to the same part of the same file. This will result in something called a merge conflict. Normally, Git can automatically merge files for us. But when we have a merge conflict, it will need a little help to figure out what to do. To see how this would look, let's edit the free_memory.py file in the master branch and replace the pass statement with a comment about what the main function should do. Cool. We made the change, so let's save it and commit it back to our master branch. Next, let's check out the even better feature branch and make a change in the same place. In this case, we will replace the call to pass with a call to print, saying that everything is okay. Now, we'll save this other change and commit it to this branch. We are primed for chaos with our file all set up for a merge conflict. Let's check out the master branch again and try to merge the even better feature back into it. Git tells us it tried to automatically merge the two versions of the free memory file, but it didn't know how to do it. We can use git status to get more information about what's going on. As usual, git status gives us a lot of additional information. It tells us that we have files that are currently unmerged, and that we need to fix the conflicts or abort the merge if we decide it was a mistake. It also tells us that we need to run git add on each unmerged file to mark that the conflicts have been resolved. Let's get to work. To fix the conflict, let's open up free_memory.py. Thankfully, Git has added some information to our files to tell us which parts of the code are conflicting. The unmerged content of the file at head. Remember, in this case, head points to master is the docstring stating what the main function should do. The unmerged content of the file in the even better feature branch is the call to the print function. It's up to us to decide which one to keep or if we should change the contents of the file altogether. In this case, we'll keep both statements and delete the merger markers. Now that we've fixed the conflict, we'll mark it as resolved by running git add on the file, and then call the git status to see how our merge is doing. See how Git now tells us that all conflicts have been resolved. Now we just need to call git commit to wrap up the merge. The comments that git commit shows us look different than other commits. That's because this is a merge and Git tells us so. It also tells us which file had conflicts which have now been resolved. The commit already has a description saying that it's merging the other branch. This description was automatically created when we called the git merge command, but we can add on to this description if we want. For example, we can say that we're keeping the lines from both branches and then just save and exit as usual. The merge conflict is resolved. To see what the commit history looks like now, we'll use a couple of handy options to the git log command. -- graph for seeing the commits as a graph, and -- one line to only see one line per commit. This format helps us better understand the history of our commits and how merges have occurred. We can see the new commit that was added and also the two separate commits that we merged, one coming from the master branch and the other coming from the even better feature branch. We can also see that master is pointing to the merge commit, but even better feature is still pointing to the previous one. In our example, resolving the conflict was straightforward and easy, but in the real world, this won't always be the case. Merge conflicts can sometimes be tricky, complicated, and spread across multiple files. If you want to throw the merge away and start over, you can use the git merge -- abort command as an escape hatch. This will stop the merge and reset the files in your working tree back to the previous commit before the merge ever happened. So by now you know how to create, delete, and switch between branches in Git. You've also seen that each branch represents a pointer to a commit in a sequence of independent snapshots. You know how to merge these commits back into the main trunk by using the git merge command. Next, we'll learn a load of new things related to GitHub and remote repositories. Up till now, we've learned a lot of interesting and complex techniques on how to use Git locally. We started with the very basic Git workflow for modifying files, staging the changes, and then committing them. We then looked at other things we can do with Git, like deleting or renaming files, getting more information about commits, or skipping the staging area altogether. Next, we saw how to undo staged, unstaged, or committed changes in our Git repositories. Finally, we learned a bit about how to work with different branches, like how to merge changes from separate branches. Now, we'll learn a load of new things related to GitHub and remote repositories. We'll first talk about what GitHub is and why it matters, and then we'll dive into how to work with GitHub and other remote repositories. Being able to use remote repositories allows us to effectively collaborate with others. Earlier this videos, we called out that Git is a distributed version control system. Distributed means that each developer has a copy of the whole repository on their local machine. Each copy is a peer of the others, but we can host one of these copies on a server and then use it as a remote repository for the other copies. This lets us synchronize work between copies through this server. Any of us can create a Git server like this one, and many companies have similar internal services. We will use an online service. We will use GitHub. GitHub is a web-based Git repository hosting service. On top of the version control functionality of Git, GitHub includes extra features like bug tracking, wikis, and task management. GitHub lets us share and access repositories on the web and copy or clone them to our local computer so we can work on them. To use GitHub, the first thing you need to do is create an account if you don't have one already. Signing up online is free and relatively simple. Once you've done that, you can either create your own repos or contribute to repos from other projects. If you don't have a GitHub account yet, now is a good time to create one. Visit github.com to sign up for their service. Let's do this now, going step by step. We'll start by clicking the Create a Repository link on the left. This will take us to the repo creation wizard. The wizard is pretty straightforward. The first thing we need to do is give a name for our repo. We'll call this repo Health Checks. After that comes a description of what the repo will be used for. We'll say that it'll be used for scripts that check the health of our computers. Then we need to select whether we want the repo to be public or private. We'll go with private for now. Finally, the wizard can help us get started with some few initialization files like a README, a gitignore, or a license file. We'll go with just the README for now, and then create the repo. Using the wizard, we created the repo and have a fresh remote repository ready to go. Let's get to work. First step is to create a local copy of the repository. We'll do that by using the git clone command followed by the URL of the repo. GitHub conveniently lets us copy the URL from our repo from the interface so that we don't have to type it. We're now ready to clone the repo into our computer. We'll do that by calling git clone and pasting the URL we copied. Just like that, we've downloaded a copy of the remote repository from GitHub onto the local machine. This means that we can perform all the Git actions that we've learned up till now. Since the repo is called Health Checks, a directory with that name was automatically created for us and now has the working tree of the repository in it. So let's change that directory and look at the contents. Our repo is basically empty. It only has the README file that GitHub created for us. This file is in a special format called Markdown. Let's add a bit more content to it. We've changed this file. What do we need to do now? We need to stage the change and commit it. We've seen a couple of different ways to do that. Let's use our shortcuts to do this in just one command. Okay, we've modified our README file, but we've seen all this before. We got to a remote repository set up on GitHub, so let's use it. We can send our changes to that remote repository by using the git push command, which will gather all the snapshots we've taken and send them to the remote repository. In this case, we've only taken one snapshot. We'll talk more about what's going on behind the scenes with git push and remote repositories later. But the mechanics are pretty simple. To push our modified README up to GitHub, we'll just call git push. After that, we see a bunch of messages from Git related to the push. When we access our project, we see the contents of the README file. So if we check our repository on GitHub, we should see the updated message. Pretty cool, right? We've taken the local changes on our computer and pushed them out to a remote repository hosted on GitHub. Now, let's use a credential helper which caches our credentials for a time window so that we don't need to enter our password. Git already comes with a credential helper baked in. We just need to enable it. We do that by calling git config global credential.helper cache. We can try another git command. Git pull, which is the command we use to retrieve new changes from the repository. With that, we've seen how to create repositories on GitHub, clone our remote repository, push changes to it, and pull changes from it. To understand remote repositories and Git's distributed nature a bit better, imagine you're working together with some friends to design a computer game. Each of you has a different portion of the game you're responsible for. One person is designing the levels, another the characters, while others are writing the code for the graphics, physics, and gameplay. All these areas will have to come together into a single place for the final product. Although your friends might work on their parts by themselves from time to time, everyone needs to send out progress updates to let each other know what they've been working on. You will then need to combine their work into your own portion of the project to make sure it's all compatible. Using Git to manage a project helps us collaborate successfully. Everyone will develop their piece of the project independently in their own local repositories, maybe even using separate branches. Alongside the local development branches like master, Git keeps copies of the commits that have been submitted to the remote repository in separate branches. If someone has updated a repository since the last time you synchronized your local copy, Git will tell you that it's time to do an update. If you have your own local changes when you pull down the code from the remote repo, you might need to fix merge conflicts before you can push your own changes. In this way, Git lets multiple people work on the same project at the same time. When pulling new code, it will merge the changes automatically if possible, or will tell us to manually perform the integrating if there are conflicts. So when working with remotes, the workflow for making changes has some extra steps. We'll still modify, stage, and commit our local changes. After committing, we'll fetch any new changes from the remote repo, manually merge if necessary, and only then we'll push our changes to the remote repo. When we call a git clone to get a local copy of a remote repository, Git sets up that remote repository with the default origin name. We can look at the configuration for that remote by running git remote-v in the directory of the repo. Here we see the URLs associated with the origin remote. There are two URLs. One will be used to fetch data from the remote repository, and the other one to push data to that remote repo. If we want to get even more information about our remote, we can call get remote show origin. There's a ton of information here, and we don't need all of it right now. We can see the fetch and push URLs that we saw before, and the local and remote branches too. For now, we only have a main branch that exists locally and remotely. So the information here seems a bit repetitive. Once you start having more branches, especially different branches in the local and remote repo, this information starts becoming more complex. Whenever we're operating with remotes, Git uses remote branches to keep copies of the data that's stored in the remote repository. We could have a look at the remote branches that our Git repo is currently tracking by running git branch -r. These branches are read-only. We can look at the commit history like we would with local branches, but we can't make any changes to them directly. To modify their contents, we'll have to go through the workflow we called out before. First, we pull any new changes to our local branch, then merge them with our changes and push our changes to the repo. We can also use git status to check the status of our changes in remote branches as well. Now that we're working with a remote repository, git status gives us additional information. It tells us that our branch is up to date with the origin/main branch, which means that the main branch in the remote repository called origin has the same commits as our local main branch. But what if it wasn't up to date? So first, let's look at the output of the git remote show origin command. Check out how it says that the local branches are out of date. This happens when there were commits done to the repo that aren't yet reflected locally. Git doesn't keep remote and local branches in sync automatically. It waits until we execute commands to move data around when we're ready. To sync the data, we use the git fetch command. This command copies the commits done in the remote repository to the remote branches, so we can see what other people have committed. Let's call it now and see what happens. Fetch content is downloaded to the remote branches on our repository, so it's not automatically mirrored to our local branches. We can run git checkout on these branches to see the working tree, and we can run git log to see the commit history. Let's look at the current commits in the remote repo by running git log origin/main. Looking at this output, we can see that the remote origin/branch is pointing to the latest commit, while the local main branch is pointing to the previous commit we made earlier on. Let's see what happens if we run git status now. Git status helpfully tells us that there's a commit that we don't have in our branch. It does this by letting us know our branches behind their remote origin/main branch. If we want to integrate the branches into our master branch, we can perform a merge operation, which merges the origin/main branch into our local main branch. To do that, we'll call git merge origin/main. Great. We've merged the changes of the main branch of the remote repository into our local branch. See how Git tells us that the code was integrated using fast forward? It also shows that two files were added, check free space and freememory.py. If we look at the log output on our branch now, we should see the new commit. We see that now our main branch is up to date with the remote origin/main branch. With that, we've updated our branch to the latest changes. We can use git fetch like this to review the changes that happen in the remote repository. If we're happy with them, we can use git merge to integrate them into the local branch. Since fetching and merging are so common, Git gives us the git pull command that does both for us. Running git pull will fetch the remote copy of the current branch and automatically try to merge it into the current local branch. Let's see if there have been any new changes made to the repository. We'll run git pull and see what changes we get. If you look closely at this output, you'll see that it includes the output of the fetch and merge commands that we saw earlier. First, git fetched the updated contents from the remote repository, and then it did a fast-forward merge to the local main branch. we'll see that the check free space file was updated as well. We can look at the changes by using git log -p-1. We see that an empty function called check disk full was added to the check free space file. What if we found a new branch when we call git pull command? Let's try this out. We see that there is a new remote branch called experimental. Your friend told you that they've started working on a new feature in that branch. Let's check out the output of git remote show origin and see what it says about that new branch. We see that there's a new remote branch called experimental, which we don't have a local branch for yet. To create a local branch for it, we can run git checkout experimental. When we checked out the experimental branch, Git automatically copied the contents of the remote branch into the local branch. The working tree has been updated to the contents of the experimental branch. Now we're all set to work on the experimental feature together with our colleague. Next, we'll look at what happens when we try to push changes, especially when our changes generate conflicts. As we called up before, when using Git to work on a new feature or a big refactor of some kind, it's recommended best practice to create separate branches. There are many advantages to doing this. For example, it might take you a while to finish a new feature, and in the meantime, there could be a critical bug that needs fixing in the main branch of the code. By having separate branches, you can fix the bug in the main branch, release a new version, and then go back to working on your feature without having to integrate your code before it's ready. Another advantage of working in separate branches is that you could even release 2 or more versions out of the same tree, one being the stable version and the other being the beta version. That way, any disruptive changes can be tested on a few users or computers before they're fully released. So let's start a new branch to work on a small refactor of our code. You could create the branch first, and then check it out. Or we could just create it and check it out with git checkout -b and the new branch name. We're ready to start working on our refactor. Let's open up the file and have a look at it. We've noticed there's a pattern of repeating code in our check free space.py script. For each check that we call, we check if it returns true or false. When it returns true, we print an error and exit. If we add a new check, we'll have to repeat this pattern again. On top of the repeated pattern, if a computer has more than one problem, only the error for the first one will be printed. So let's refactor our code to avoid the duplication and print all relevant errors. We'll do it step by step, making each commit self-contained. The first thing we'll do is create a function that checks if the disk is full without any parameters, so it matches the pattern. This new wrapper function will pass the right parameters for us. Then we'll change the code to call this function instead. We'll also change the error message to something more accurate. We've changed the function. Let's save and test our code. Awesome. It's working. Let's commit the change. Now, we're ready for the next step in our refactor. To avoid code repetition, we'll create a list containing the names of the functions that we want to call, and then message to print if the function succeeds. After that, we'll add a for loop that iterates over the list of checks and messages. Then we'll call check, and if the return value is true, print the message and exit with an error code of 1. After doing that, we can delete the old code that we've already replaced. this change made, let's save once again and test that our script still runs. Yes, it's still working. Let's commit the new change. By now, we've refactored our code to avoid code duplication. The current code does the same as the old code. Once we're ready to add new checks, we can do that by adding the function name and error message to the list of checks. The last change that we want to do is to let our script show more than one message if more than one check is failing. To do that, we add a Boolean variable called everythingOK before the iteration. Change this variable to false if one of the checks find a problem, and then exit with an error code only after having done all the checks. All right, one last time. Let's save and test to see if this works. And now let's do a file commit for this change. With that, we have 3 commits in our refactor branch. Before we merge any of this into the master branch, we want to push this into the remote repo so that our collaborators can view the code, test it, and let us know if it's ready for merging. The first time we push a branch to a remote repo, we need to add a few more parameters to the git push command. We'll need to add the -u flag to create the branch upstream, which is another way of referring to remote repositories. We'll also have to say that we want to push this to the origin repo and that we're pushing the refactor branch. That's a lot of information that Git's giving us. It's telling us if we want, we can create a pull request. Now, we see that a new refactor branch has been created in the remote repo, which is what we wanted. So now that our branch is pushed to the remote repo, it can be reviewed by our collaborators. Assuming they say it's okay, how should this branch get merged back into the main branch? We mentioned that once our branch has been properly reviewed and tested, it can get merged back into the master branch. This can be done by us or by someone else. One option is to use the git merge command that we discussed earlier. Another option is to use the git rebase command. Rebasing means changing the base commit that's used for our branch. So how do we do it? We run the command git rebase, followed by the branch that we want to set as the new base. When we do this, Git will try to replay our commits after the latest commit in that branch. This will work automatically if the changes are made in different parts of the files, but will require manual intervention if the changes were made in other files. Let's check out this process by rebasing our refactor branch onto the master branch. First, we'll check out the main branch and pull the latest changes in the remote repo. Git tells us that it's updated the main branch with some changes that our colleague had made. At this point, the changes that we have in the refactor branch can no longer be merged through fast forwarding into the main branch. That's because there's now an extra commit in the main that's not present in the refactor. Let's see how this looks by asking the log command to show us the current graph of all branches. It might take a bit to follow everything that's going on with this graph, but it can be really useful to understand complex history trees. As you can see, the refactor branch has 3 commits before the common ancestor, with the current commit that's at the head of the main branch. If we merge our branch now, it would cause a 3-way merge, but we want to keep our history linear. We'll do this with a rebase of the refactor against main. As usual, Git gives us a bunch of helpful information. It says that it rewound head and replayed our work on top of it. And luckily, everything succeeded. Let's look at the output of git log --graph -one line for our branch right now. Now we can see the main branch and linear history with our list of commits. We're ready to merge our commits back onto the main trunk of our repo and have this fast forwarded. To do that, we'll check out the main branch and merge the refactor branch. We were able to merge our branch through a fast-forward merge and keep our history linear. We're now done with our refactor and can get rid of that branch, both remotely and locally. To remove the remote branch, we'll call git push-delete origin refactor. To remove the local branch, we'll call git branch-d refactor. We're done with our refactor. We can now push changes back into the remote repo. Alright, we've just gone through an example using the git rebase command. We had a feature branch created against an older commit from main. So we rebased our feature branch against the latest commit from main and then merged the feature branch back into main. We've looked at a lot of things we can do with Git and remote repositories. It's worth spending some time talking about best practices for collaborating with others. It's a good idea to always synchronize your branches before starting any work on your own. That way, whenever you start changing code, you know that you're starting from the most recent version and you minimize the chances of conflicts or the need for rebasing. Another common practice is to try and avoid having very large changes that modify a lot of different things. On top of that, if you remember to push your changes often and pull before doing any work, you reduce the chances of getting conflict. We called out already that when working on a big change, it makes sense to have a separate feature branch. This lets you work on new changes while still enabling you to fix bugs in the other branch. I'll make the final merge of the feature branch easier. It makes sense to regularly merge changes made on the master branch back onto the feature branch. This way, we won't end up with a huge number of merge conflicts when the final merge time comes around. If you need to maintain more than one version of a project at the same time, it's common practice to have the latest version of the project in the master branch and a stable version of the project on a separate branch. We looked at how we can use rebase to make sure our history is linear. Rebasing can help a lot with identifying bugs, but use it with caution. Whenever we do a rebase, we're rewriting the history of our branch. The old commits get replaced with new commits, so they'll be based on different snapshots than the ones we had before, and they'll have completely different hash sums. This works fine for local changes, but can cause a lot of trouble for changes that have been published and downloaded by other collaborators. So as a general rule, you shouldn't rebase changes that have been pushed to remote repos. The Git server will automatically reject pushes that attempt to rewrite the history of the branch. It's possible to force Git to accept the change, but it's not a great idea unless you really know what the implications will be. In our feature branch example, we rebased the branch, merged it to the main, and then deleted the old one. That way, we didn't push the rebase changes to the refactor branch, only to the main branch that hadn't seen those changes before. Early in our Git journey, we mentioned that having good commit messages is important. It's already important when you're working alone since good commit messages help the future you understand what's going on, but it's even more important when you're collaborating with others since it gives your collaborators more context on why you made the change and can help them understand how to solve conflicts when necessary. So commit to being a good collaborator and remember to add those commit messages. You have unlocked Git and GitHub with Databits Central. If this helped, smash that like button, subscribe, and ring the bell. New videos are consistently being released to keep your skills sharp. A Git cheat sheet in the description. What's your Git struggle? Let me know in the comments. Thanks for watching, keep coding, and see you soon.